I'm Prasanna, and I'm a postdoctoral researcher in the group headed by Professor Arkady Fedorov in the University of Queensland in Brisbane. We're under this center called EQUIS, which is the Engineering Quantum Systems. And the particular poster of concern here is that we're looking into testing the ultimate limits of timekeeping. So before we look into timekeeping itself, it's a good idea to see what makes a clock, as in a timekeeper. So there's particular requirements that we demand. The first of which is that it counts forwards in time. I think that's pretty natural. And that implies that the underlying physics must be an irreversible process. And if you've done a bit of quantum mechanics, you realize if it's an irreversible process, it has to be dissipative. You're sort of losing information to the external environment. So a clock will require us to provide energy to compensate for the dissipation. And a third requirement, which is a bit of a subtle one, is that we want this clock to be indefinitely ticking. And this implies that typically we have to have some kind of nonlinearity in it such that we could form some kind of a limit cycle so that if we turn it on, we'll just keep indefinitely ticking. So when we went about this, then we thought, okay, what's the simplest possible clock we could make to actually test what the ultimate limits are? Well, we're quantum physicists here. So the two-level system, the qubit, is actually one of the simplest systems we know. So how do we turn a qubit into a clock? So the way we do it is we first utilize a superconducting transmon qubit in this case, which is actually one of the more popular platforms right now, so similar to what IBM and Google use. And so let's go through the list of requirements that I've put forward. So first of all, the qubit has a T1 decay time, as in it will decay to the ground state if I put it in the excited state, because it's coupled to the environment. So by definition, it is irreversible because it's dissipative in this case. So to provide compensation for this dissipation, to provide energy into the system, we will drive the qubit. So what we'll be doing is rotating the qubit about the x-axis of the Bloch sphere. So we'll continuously be driving it. And while we're driving it, we'll actually be measuring the qubit simultaneously. So typically with qubit experiments, what you would know is the protocol is like we initialize, we do an operation, like a rotation, and then we measure. Here, what we're doing is actually doing the operation and the measurement simultaneously. And in doing so, we basically, we compensate for the energy due to dissipation. And the measurement operation itself is actually a nonlinear operation. So this will basically induce a limit cycle. So it'll keep indefinitely ticking. Now, the interesting property of our clock, however, is this limit cycle is actually a function of how strongly we measure it. So in a conventional clock, like the physics of the clock is basically defined by whatever the underlying mechanisms are. It doesn't really care too much about how you're looking at it. But this particular clock, depending on how you look at it and measure it, will actually change its dynamics. So in this particular case, what we have is that if we weakly measure it, while we drive it and rotate it about the Bloch sphere, we can actually track its trajectory in a weak sense. So we can actually start to see the oscillations and actually track the population of the qubit. When we measure strongly, however, what we find is that we start to collapse it into its eigenstates. So it'll basically only give outputs that are either 0 or 1. So you start getting this nice random telegraph signal. Given these particular properties, then the next thing we looked into was basically, okay, what are the limits of the accuracy in this clock? So, what will limit its timekeeping accuracy? So typically, if you look in the field, they'll say, well, it's to do with temperature and the entropy production, which is pretty natural in its sense. But the problem with this particular thing is that our qubit system is a superconducting transmon, and it's basically at close to 0 temperature. So we can't really just blindly apply the second law of thermodynamics and go like, oh, the entropy production is proportional to temperature. No, it doesn't work. So what we have to do instead is utilize this new thing called the kinetic uncertainty relation. So basically just read our paper on that. There's a lot of nice theory behind it. But the take-home message is basically saying that the clock accuracy is bounded by the quantum Fisher information. So in a very simple sense, what that means is that the amount of information that we obtain from this qubit in measuring the clock ticks, the more accurate it becomes. So in this case, what that basically means is that if we drive it harder so it ticks faster, we basically end up getting more information out, and therefore the clock can actually get more accurate in that case. And we actually found that, from the analysis of our clock ticks in both the oscillatory regime and the quantum jump regime, that it indeed satisfied this particular inequality, that the accuracy is indeed bound by the quantum Fisher information. So it's a sort of an ultimate bound that we cannot surpass. So ultimately, what we've demonstrated is a very simple clock that was constructed from a simple two-level system, a qubit, and we were able to then actually test the ultimate bounds of timekeeping beyond that of just like the thermal bounds that we'd usually see. Because now in this particular case, we're actually limited by the measurement-induced back action. So it's a very quantum mechanical phenomenon here.